Okay, if that's all the administrative things, let's do the sciencey things. So my warm up for you guys today, I'm doing an individualized warm up on ionic bonding because I went over this in tutoring and we did some work, right? We did some work yesterday. And I think that it would benefit if we revisited this briefly for 5 or 10 minutes one more time. Then we're going to jump into covalents. Okay. So right now we are doing ionics. So barium phosphide is ionic. How do I know? Esty, how do I know that's ionic? How can I tell?
I'm not sure.
Okay. What makes up a metal and a non-metal? I'm sorry, I just said the answer. Oh my gosh, what is wrong with me? What makes up an ionic compound? What two types?
Metals and non-metals.
Oh my gosh, how did you know that? That's amazing, right? Oh my God, I'm so lame. Anyway, yes, metals and non-metals. So if I look and I see barium phosphide, I see, oh, barium is a metal. It's in the first two groups, right? It's a metal. Phosphorus, that's a non-metal. So therefore, it's barium phosphide. It is an ionic compound because it's a metal and a non-metal. So even if I didn't tell you it was ionic, you can look at what it's made of and then you will know it's ionic, okay? Covalent is just two nonmetals, okay? So that's how you can differentiate by looking at the actual components. Thank you, Esty. Charles, your picture is so sad. What is with that? Oh my goodness, just noticed. Anyway, sorry.
Well, he just didn't get his drink in the show. So, I mean, I think it's all right.
Yeah, I think he'll be all right. He didn't get his drink in the show. It's funny. Oh man, I haven't watched SpongeBob in ages. Okay, so Dia, back to science things. I got totally sidetracked. Totally. Okay, Dia, where do I start with this concept? So I'm going to go here so I have lots of room. Where do I start? What do I do?
Would you first see if it has a positive or negative charge, like when you put the brackets?
Yeah, we can draw the Lewis dot structure. You don't have to draw the Lewis dot structure, but we will for these to practice. Another thing we should know is that if this is a metal and non-metal, the first one is always going to be positive. The second one's always going to be negative because they're based on charge. That's why ionic things happen, is because they're electrically attracted. Because the electron moved, we now have opposite charges, and those charges keep us together. We're not actually sharing the electron. We're just highly attracted. Okay. So give me 1 second. I have to respond to a private comment. Okay, all right, cool. So now, yes, we can do the bracket. So show me how to do it for barium. Go ahead and go through it, Dia.
So you put brackets and then BA.
Okay. What do I write?
And then it would be a +2.
Which one goes first?
Oh, the 2 plus, sorry.
Yes, number goes first. Number goes first. Number goes first. Number goes first. Number goes first, right? Number goes first. So we have BA 2 plus. Beautiful. I wrote it really big for some reason. That's fine. It's totally cool. All right, I'm gonna have someone else help me with the next one. Lucas, how do you do phosphide?
The brackets and then 2 minus.
It's 3 minus. What else do I gotta draw? What's this one missing?
The dot.
Yeah, all the Lewis dots, all the Lewis dots. Okay, so we have Lewis dots around the whole thing because let's look at why that is, okay? Phosphorus is in group 5, so it has 5 valence electrons. So we are adding 3 more electrons to get to 8 because that is the least amount of steps to pretend to be a noble gas. It would be more steps to pretend to be neon. So we're not going to pretend to be neon by shedding. We're going to pretend to be argon by filling. So that's why this one has dots that are full. Barium has 2 valence electrons. It's down here. Okay, so it has 2 valence electrons. So it's actually going to erase its 2 valence electrons to pretend to be xenon. So it's going to go this way instead of trying to fill its shell and pretend to be radon. Ooh, that was really bad. Pretend to be radon. Okay, so That is why this one is 2+, because we are shedding electrons. So now the protons are winning by 2. This one, we're gaining 3 electrons. So the electrons are winning by 3. Okay. Don't let the words gain and lose throw you off, because that's how math normally works in math class. Okay. All right.
Wait, so where do the 3 electrons for the phosphorus come from?
Ah, that is the crux of the whole thing. So this is an ionic bond, right? So we're talking about transferring electrons from one to the other. So the whole reason this problem exists is because ions will only bond in a ratio in which the electrons can be transferred and accepted without gaining or losing any, right? So barium's electrons that it lost physically went to phosphorus. Okay.
Yeah, I understand that, but how does he get 3 instead of 2?
Right. So that's the part I'm getting to. So that can't happen. That's impossible, right? So what is possible? I'm gonna have you do the next part. I was just about to ask this question anyway. So what can I do? If I can't join in a 1-to-1 ratio, what do I have to figure out? Joining in a 1-to-1 is impossible. I only give 2 and I accept 3. That's not real. That's not a thing.
So then you have to have another atom, like an element from like the alkali thing.
Alkali metals? No. So we're only going to be joining barium and phosphorus and barium phosphide. These are the only 2 things present. So how do we accomplish every barium?
Oh, okay. So you have more than one of.
Bingo, right?
Yeah.
We have more than one. That's what was the hardest part of this whole thing, is that we have to figure out how many we need so that every electron we give has a home, and every electron that was received came from somewhere. Like the whole crux of this is that the electrons have to have a place to go. So your question was literally like the perfect seed for the whole issue. So thank you for that. That was like literally the perfect question I could have asked for. Love it. Okay. So what number do both of these multiply to? Audrey.
Sorry, can you repeat the question? I swear I was paying attention.
You're fine. So 2+ and 3-.
Oh, 6. Hi.
They both go to 6, right? So we can do 6+ and 6-. And if we combine those, that gets us to 0. So all that addition, or this math problem, is showing us is that 6 electrons were lost, 6 electrons were gained. So there is no electrons left over. That's what this math means physically. So for barium, if we have 2+ and we need 6+, that means we need 3 bariums. And if we have 3- and we need 6-, that means we need 2 phosphorus. So the chemical equation would be Ba3P2. Okay. If you don't want to write all of that jazz and you're just like, I don't want to draw the Lewis dots, like I know so the question asked for them. But if you wrote Ba2+ and P3-, you could do this whole thing where you say, okay, 2+ and 3-, those don't add to 0 yet. Okay. So now this adds to +6, this adds to -6, everything in the triangle goes to 0. This is just a visual way to do it. When I'm looking at the subscripts, okay, this 3 is because there are 1, 2, 3 bariums. It is not the charge, it is the count. Everything is a count, okay? This 2 is because there are 1, 2 phosphides. It is not the charge, it is the count. That is the next most missed answer, okay? I have people hitting me up in the chat with issues. Yes, that's okay, Sonali. All right, so we would need 3 bariums and 2 phosphides. So last question, we have the chemical formula. We know how many of which we need. Sonali, which one is the cation?
The 3.
Which element? So I know.
Barium.
Yes, barium is the cation. Why?
Because you lose electrons.
Yep, it's the positive charge. So cations are positive like a cat, positive, right? And anions are negative every time. Okay. All right. would you choose some, okay, what would you choose if something has 4 valence electron, gaining 4 or losing 4? So the trick question to that is that it would depend on the electronegativity, but most times 4 is going to share covalently because see, carbon is non-metal, right? So everything else in here is metal and they have similar electronegativity. So they're not going to transfer ionically, right? So they aren't really going to do ionics unless they're lead or fluorium, because these ones are so heavy, or tin maybe. They're so big. They have so many electrons that all of the internal electrons, it has 82 electrons in its neutral state. So think there's literally like, there's 6 less. So there's 76 electrons chilling inside underneath the valence shell. So those electrons on the outside have an issue. Sometimes they can, sometimes I can lose 2, sometimes I can lose 4. And that was in QC 4.2 when you saw the one that's group 15 and it had the 3+ and the 2 still on there. That was showing you what bismuth does sometimes. But with these guys, it's kind of weird. And I'm not going to ask you to show me a bond with these guys ever until you're in AP or IB, because it is real funky. Okay. And you have to understand d orbital really well. And we don't do a lot of stuff with transition metals until an upper level. But the very short, simplified answer to a very long question is that it will always end up being positive, because by the time it's big enough to be positive, these are metals, and metals always lose their electrons. Does that make sense? But it's going to be mostly electronegativity. Like if it's super electronegative, it'll take all 4. If it's not as electronegative, it'll take 2, kind of thing. I know that's a real bad answer to a really great question, and I'm trying real hard. Okay, awesome. That was an amazing. I love that you're thinking that way though. That was just like, poof, I love it. You guys always blow me away. You guys like surprise me that you think ahead like that. And I love it. I love being surprised by you all the time. It makes me really happy. Metalloids. Yes, metalloids are the ones that are here on the diagonal. Like they're like here. Metalloids are ones that have properties of both metals and non-metals. And I'm not going to ask you about those either, because again, they get real funky. Okay. All right. Let's go into covalent bonding. If there's no more questions about ionic, let me make sure there's no more questions about this. Okay. Any more questions about this? No? Okay. All right. Covalent bonding. So I want you to take a look at this picture, examine it. If you have to lean in to see it, go ahead and do that, because I'm about to ask one of you to tell me what's happening in this picture, and we don't know who it's going to be. About 10 more seconds. Look at the fluorines. Look at the electron dots. See what's happening. Look at the hydrogen, oxygen. Look at the electron dots. And Akshar, explain fluorine to me. What's happening with this guy? What is happening here? What is covalent bonding?
2 different, well, usually it's 2 different non-metals.
Yep, it's 2 nonmetals, so we know that. Okay, it's 2 nonmetals because both fluorine is a nonmetal and it's 2 of itself. That's going to be true for covalent. So covalent is non-metal bonding. Okay, awesome. Someone else, thank you, Akshar. Gus, tell me what the electrons are doing.
They're being shared between both of them.
Right. So this fluorine needs 1, has 1, needs 1. This fluorine has 1, needs 1. So they decide, hey, if we each have 1 extra without a buddy, why don't we pair those up and become a bond? And that's what you see is the line in your notes. That means 2 electrons. Okay. So it's a bond. So we decided to share. An example from my real life is when I was in high school. Okay. Remember, I grew up in Detroit and things, whatever. Parents didn't get me a car. It was all on me. I've been working since I was legally working since I was 14, illegally longer, but admitting to crimes in a recording. Let's go. Anyway, so I worked as an underage person. We had money saved up. So we had the choice where each of us could get a really crappy car and potentially have lots more money to sink into it. Or since we're only a year and 9 days apart, we were like, hey, we're both going to be here. And by the time you leave for college, it's not really going to matter. We have most of the same friends. We only need the car to get to and from school. We go to the same school. Why don't we pool our money and get a nicer car? And then we share it. So we were both happier because we got a car that was reliable, that we didn't have to worry about breaking down, but we shared our money and paid in cash. Okay. And then we gave it to my little brother when we graduated. But that was what we decided to do. So we could have two situations where we were both not really happy, but kind of had what we needed, but not all the way because it didn't really serve the purpose if it's that crappy. But if we shared, we ended up both being happier. That's exactly what's happening with covalent bonding. Sharing is caring, okay? With this hydrogen forms the one bond. Now this is accurate. There are no more electrons on hydrogen, okay? This is how it works. Hydrogen gets 2 electrons and it's like done, son. So Charles, why might that be? Why might hydrogen be odd like that?
Because it only has 1 valence shell and it only needs 2 instead of 8.
Yeah, so take a look. Hydrogen is in the 1s orbital, and it only has the 1s orbital in its valence shell. So there are only space for 2 electrons in its valence shell. This is why in biology, if you remember all the way back to like last year, whenever you took it, right? If you remember all the way to biology and they said water can like cut molecules and put molecules together and it does all the weird stuff, it's because hydrogen is like an end cap. If you have a long molecule and you bond to hydrogen, hydrogen can only bond one thing. So it's like a period to a molecule. Hey, this oxygen, this side is end capped. Nothing else can bond here. This side is end capped. Nothing else can bond here, right? So nothing could continue this way. So it keeps the molecules smaller. That's how it cuts molecules. So just to put the chemistry connection into biology class from last year, that's what was happening, okay? All right. So determining how we share can be difficult, okay? So normally when you learn Lewis structures, I say, okay, draw the Lewis structure for CH4, methane. And you guys draw C's and H's and you just kind of like draw lines and dots until it kind of looks okay. And then you're like, I think that's right. And you send it in and you're not really sure. Or you go to Grandmaster Google and ask for that, right? So instead, I want to show you a method because not only are you going to have a video explanation for this, but this is a really important concept that you know. And also a note about Google. Google is kind of like, Google is a popularity contest, not a correction contest, right? So Google will show you what most people have clicked on, okay? Not what's guaranteed to be right. It only looks at popularity, not correctness. I cannot tell you the number of times I've had a student Google a molecule and Google tells them wrong because even that little box on the top from Google that says this is the answer and it shows you a preview is just from the website that was most popular. It's not guaranteed to be right. And there are a lot of chemistry professors teaching virtually that have gone on Chegg and other places and purposely given wrong answers so they can see students cheating. Not that I'm going to check, but there's a lot of chemistry professors. I can show you the whole Facebook thread. I could throw it up on the screen right now. I can show you the whole Facebook thread that they're drawing things wrong on purpose, like things with hydrogen with double bonds and things like that so they can catch kids cheating. So your guarantee for Google is not right. And oh my God, was that a little kitten behind you, Kai? Or was that a little puppy? I'm so sorry. I saw an animal. That was so cute.
Sorry, yeah, that's my dog back there, Lola.
Oh my goodness, he's so little. Sorry. So anyway, yeah, so just so you know, Google is probably going to be wrong because there's a bunch of angry college professors that are doing some really wicked things. And it's been really funny to watch actually in the Facebook group. It's pretty funny. Anyway, so I'm going to show you the way to do it. So you know for 100% sure you got the right answer every single time. Okay, so sound good to everybody? Okay, so if we're looking at PBr3, okay, that's phosphorus and bromine. How many phosphorus are there? Evangelina, how many phosphorus atoms are in this molecule?
1.
All right, cool. We have 1 phosphorus molecule, and I highly encourage all of you to write along as you're doing this. If you don't like writing in your notebook or using up paper, if you put a sheet of paper inside a page protector and use an expo marker, it's just like a whiteboard and it's awesome, okay? So we have 1 phosphorus. Victoria V, how many bromines do we have? 3. So if we had 1 phosphorus plus 3 bromines, this is what the math equation would look like for that molecule, right? Pretend it's algebra and they're X and Y's. We have phosphorus, 1 phosphorus plus 3 bromines equals our molecule. So our first step is to find the number of valence electrons available to us to bond. Okay, so Carter, what are the only types of electrons we care about here in bonding?
Valence electrons.
The valence electrons. So the atomic number where it's a neutral atom and they're the same, that's not a thing here. We're only looking at valence electrons, which is group number. So next person. I'm going to skip you because you said you weren't feeling great today. Give you a break. You. What is the number of valence electrons for phosphorus? Remember, all these are going to be in the upper right too, because we're looking at nonmetals.
Is it
What's the-
3?
Is it 3? So 3, it would be the charge if it was an ion. We're asking for the valence electrons, what's physically present in neutral atom. So in covalent, we're not gaining or losing anything. We have exactly what we have, and we're not even looking at what's easier. We're just sharing what we've got. So how many does protein have, listen to me, phosphorus have to share? How many valence electrons does it have to contribute?
Would it be 5?
Yes, it's going to be 5 because it's in group 15 or 5A or VA, which is Roman numeral 5A, showing that it's 5 valence electrons for phosphorus. That's where that came from. Plus our 3 atoms of bromine each have how many? Megana, how many do each of those have? Each bromine. Stop. Each bromine. What is happening?
7?
Yes, each bromine. Wow, what in the world is going on here? Okay, hold on. Me and my pen are going to have a fight. Hold on. Yes, for bromine, they each have 7. So let me do this. Yes. Okay. So 3 times 7, that's 21 plus 5. That gives me 26 valence electrons to use for my molecule. Not an electron more, not an electron less. So when I am done drawing, what should I do? When I get all the way to the end of the problem, what should I do? Renee.
Sorry, could you repeat the question?
Yes, I said we have 26 valence electrons to use. So when we get all the way to the end of the problem and we're done drawing, what should we do?
I'm not sure.
So say you do the drawing and you say you're done, but when I count it, you only had 24 valence electrons. Can that possibly be right?
No.
No, because we have 26 to use and we have to use all 26. Everything that has existed continues to exist. Conservation of mass, right? So at the end of the problem, how do I check to make sure I'm right?
Check to see if you have, if you could have 8 valence electrons in each.
Yep, make sure each one has 8 after we share, and we used how many total?
We used 26.
Yes, so we should have 26 valence electrons accounted for on our drawing, and everybody should have a full octet. That is how we check our work. So the most important thing you have to know is how to check your work, right? So now we have 26 valence electrons to use, but the whole purpose of sharing is to pretend to be a noble gas. So Darshan, when you have an atom, how many electrons would phosphorus want if it was by itself and in a perfect world? Like what would it want if it could be by itself and have exactly what it wanted? How many would it want?
8 valence electrons.
Yes. So the number of valence wanted, phosphorus wants 8. That's the whole reason it's doing this, right? How many does bromine want? Kai, how many does bromine want?
Sorry, can I check the notes just
Yeah.
to make sure there's no exception?
This one is not one of the exceptions.
Okay, then 8.
8, yes.
Okay.
We'll talk about exceptions at the end, okay? So the reason I say do it like a math formula like this is what if this one was hydrogen? How many does hydrogen want in a perfect world? Anybody? Spacebar.
2.
2. So if you were doing this and hydrogen existed, you'd have to put a 2 here. So just set it up like a math problem, do it the same way every time. So that way you don't have to remember when to do it and when not to do it, right? So this is 4/8. That's 32 valence electrons in a perfect world. If we didn't have to share, for everybody to have what they wanted, we would need 32 valence electrons. So Shanmathi, how do I tell how many I need to share? What do I need to do? I have 26. I want 32. How many do I need to share?
32 minus 26.
Hold on, you guys got really quiet all of a sudden. Is it me? Nope, my speaker's on. You were really quiet, baby. Can you try that again?
You would share 6 electrons.
How did you get there?
I subtracted the 32 from 26.
Yeah, so I have 26, I want 32. The difference is 6 valence electrons. Now remember what I said about a bond. Each bond is equal to 2 electrons, okay? So remember the dots are electrons. We don't actually draw it like this, so don't draw it this way, but each bond is equal to 2 electrons, okay? So when we count, this is a 2, this is a 1, okay? Just like before, the dots are always 1 electron, the lines are 2. So if each bond has 2 electrons, how many bonds would I need to share the right amount? Trisha? Trisha?
I don't know.
Okay, let me ask you a different question, okay? I have 6 shoes. How many pairs of shoes do I have? I have 6 individual shoes. How many pairs do I have?
3.
Okay, I have 6 valence electrons, okay? Each bond is a pair, right? It's a pair, it's 2. So how many bonds do I have?
3.
Right, 'cause I have 6 valence electrons, and there's 2 valence electrons per bond, right? I'm gonna write it out so you can see it just this one time, right? 6 valence electrons, there's 2 per bond. So that's 3 bonds I have to have in this molecule to satisfy it. The reason that's important is because it's not always just 1 bond. There's a possibility for 2 bonds or 3 bonds. So you want to make sure, do I need singles? Do I need doubles? So knowing the number of bonds you have to use is actually a very important piece of information. All right. Next step, Corey, we know the number of bonds, so everything else has to be single electrons. So what do I do now? What do you think? Ooh, no. What do I do now?
Hold on.
This is my molecule, right?
Could you give me a hint? I kind of forgot.
Absolutely, I love giving hints. It's one of my favorite things. So, hint time. This is our molecule. We have to decide which one's in the center and which ones go around the outside. So, which one do we draw in the center? The P or the Br3?
I think the P.
Yes, you always put the one that's kind of by itself in the center or has the most electrons available to bond. Because remember, phosphorus is sharing. It has 3 sides that have lone pairs. So if I were to draw this Lewis dot, right? Oh, no, not the ion. See, I got in the habit. If I were to draw the Lewis dot, this one has 1, 2, 3 spots available to share, where bromine only has 1 spot available to share, right? So because it would be pair, 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 and then a single electron. So this one only has 1 spot available to share. So phosphorus is going to be in the middle. When we write molecules, we usually write the central one first, usually being the keyword, okay? So we have P and we're going to write BRs around the outside. It doesn't matter which sides of the box you use. You could put them on the bottom, the side, etc. As long as you pretend phosphorus has an imaginary box and then you draw 3 around it. Okay, so just use the sides of that imaginary box we've been using. Awesome. Did that help, Corey?
Yeah.
Okay, awesome.
Thank
So
you.
Jessica, what do I do now? I have my atoms drawn. How do I draw my bonds and electrons? What do I do?
For the bonds, first just like draw the electrons for phosphorus just to visualize it.
Okay, so here's the hint I'm going to give you. This I drew so you could visualize and see what's happening. But when we draw these molecules, you're not going to like draw all the dots.
Oh,
and
it's already there.
right? So the reason we did this, so let me tell you the reason, because I know that like the video notes were slightly different. The reason we do it this way is so that way we don't have to do all the erasing and guessing and things and moving. This tells us exactly how many bonds we need. So for it to be a molecule, all of them have to be connected somehow. So the real question is, how do I connect all of these 4 molecules with only 3 lines?
Okay, so draw one line from like one bromine to the phosphorus.
Yep.
And then like, for each of them.
Right, so we did our bonds. We connected all the molecules. So what I usually do is I just connect all the atoms and then see, okay, I used 3 bonds. I only had 3 bonds. So I'm done with my bonds. All right, awesome. Thank you. I know that's tough. And guys, just so you know, I've done this now. You're the 3rd class period that's done this. Learning is uncomfortable. I am being decidedly vague, right? Because being able to embrace that odd feeling in your stomach and be slightly vulnerable and say something out loud is a skill that I think that people should teach all the time. That's how learning feels. Learning isn't easy. If it's easy, you're demonstrating, not learning. The learning part is uncomfortable when you're challenging yourself, and you should seek that feeling. Like, you know, you're improving when you feel that way and it feels yucky. And then about 10 minutes later, you don't feel that way. That's literally your emotional response telling you you learned something, and it's amazing. So embrace the suck. Just embrace that like in your stomach and know that it will pass. And that is what learning really is. And if you are going to continue in the pre-AP advanced academics world, you're going to have to get real cozy with that feeling. And that's a great thing. That's a beautiful thing. It's not a bad thing. It's just your body going, I don't know. And it's like fight or flight response happening, because that's how you've been trained to feel. You've been trained that if I don't know the answer, I get publicly shamed. And that's not what this is. Okay. So fight the feeling. It's good. It's good to be uncomfortable. Okay. Eden, I've drawn my lines. I have my atoms. What do I do now?
To be honest, I'm not really sure.
Okay, so right now I've only used 6 electrons. I have 26. So what do I do now?
You need the other 20. So you have to put the lone pairs.
Yep, lone pairs just means the side of the atom that has 2 dots instead of a line. They are alone, they are not shared, and they are in a pair. Lone pair, okay? So bromine wanted how many did we say?
They wanted 8.
So let's fill it up till it has 8. We have all the bonds, right? So we have 2, because this is representative of 2, 4, 6, 8. Remember, fill the sides of the box, the imaginary box that's there. What's this one? How would I do this one? How many does this one need?
It needs 6 more.
Yep, needs the same as the other bromine. Why does it magically erase things sometimes? Okay. And then this one does too. Okay. Am I done?
No.
Why am I not done?
Don't you still need the phosphorus?
Yes, phosphorus isn't happy yet. So what do I need to do?
You need to draw 2 more because it already has 6.
Awesome. Great. So I'm done, guys. Can drop my pen. I'm 100% sure I'm ready to go, right? Yeah? No? Kai, are you shaking your head? Why are you shaking your head? What do I got to do?
You have to double check that there are 26 electrons.
Yeah, there have been so many times, like, what if you made a little mistake, right? So you don't have to write these numbers. I'm going to physically write the numbers this time to visualize what I am counting. So that way it makes sense to you. Okay. Because, you know, I'm not in the room with you. So here there's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. That 26 was what I needed. This is the correct molecule. Again, don't actually write the numbers when you do yours. I'm just showing you where I was counting because I'm just talking at you on a screen. Okay. Yes. How did I get the dots? So the dots show up because we have 26 valence electrons, right? We have the bonds here that account for 6, but the whole point of bonding is that everybody gets a full octet. So the dots are the leftover 20 electrons that we did not represent yet in our valence shells that will satisfy the octets of each atom. Okay, so to give myself a little bit cleaner slate, I'm going to erase this in a second. So if I just had the phosphorus and the bromine like this, I know I had 26 valence electrons. I only used 6. So that's 20 valence electrons that just like disappeared like Houdini. That can't happen. These 20 valence electrons are also present. The chemical bonding does not remove electrons. This is not a nuclear equation where we're ejecting beta particles. Everything that was there is still there. So we have to find a spot for these 20. I'm not just going to put 20 dots around one bromine and be done because that's impossible, right? That can't happen because everyone wants 8. So I'm using the dots to fill the octet. So there's 2, 4, 6, 8 on each atom. Is that a better explanation? And does that answer your question? Yes, the bonds always represent 2 valence electrons. If it's a line, it's like Morse code. Line is 2, dot is 1 every single time. Not that you all know Morse code necessarily. I'm just saying dots and lines, dots and lines. Dot is always 1, line is always 2. Are there any other questions? There's 6 because for this bromine, remember we said how do we bond? How do we bond? We're sharing, right? So let's go back here. Here, these ones each have 7, but they decided to share these 2. So when I'm counting, I count, ooh, that's a really bad color choice. What am I doing with my life? I count 1, 2, 3, 4, 5, 6, 7, 8. This guy also has 1, 2, 3, 4, 5, 6, 7, 8. So these are shared. These 2 count for both atoms. So that line counts for both atoms. So when I'm here and I have Br and 6 dots, right? I count this 2 for bromine, and I also count it for phosphorus because they're sharing them. So that's why this one has 2, 4, 6, 8. 2, 4, 6, 8. It counts for each one. So those 6 dots are just what's left over from this one. This one also counts for 2. These are great questions coming from the chat. Thank you so much. Is that better? Does everyone get it? Give me a scale 1 to 10. Drop any questions. I am more than happy to go slower if you need it. Again, this is the 3rd time I've done this. So I'm kind of like preempting some questions I got when I went too fast for the first period. So if I miss anything or if I'm still going too fast, let me know. Oh, we have, so what I was going to say is this class is going to go a little longer. We usually get done at like, if you're new here, 12:25-ish is usually my like mark of we need to go soon. Because I don't want to just say, hey, read the notes and do it. Like there's a lot to explain in chemistry that's conceptual. So I planned on doing at least 2 more examples. They won't take nearly as long as that one because that was instructional. That one was me teaching you what every little thing meant. These next 2 are going to go fast. We're going to do exceptions. We only have about 10 minutes left if you'll stick around. And we'll look at the alone pairs again in the next example. So that way we can move on. Okay. So yes, we're going to do more examples. I had someone in the chat say, please do more examples. I'm absolutely doing more examples. I even have some extra ones in the bank. Wait. Don't do that. I have some extra ones in the bank in case anyone wants to hang after and do more examples because that's totally cool with me. Okay. All right. So for CF4, I want you to try to do each step on your own first. I'm going to give you about 30 seconds to start working through these steps, find the number of valence electrons, etc. So when we get down to the bonding part, that's where we're having most of our discussion. So everyone try to do the steps on their own. About 20 more seconds. 10 more seconds. All right. Oh, I see something in the chat. Oh, thank you. Someone liked my computer background. All right. So, let's see who the wheel is picking this time. Adhish, do step 1. Talk me through step 1.
So C is in group 14, so it has 4 valence electrons.
Right. So we have C has 4 valence electrons. All right. What's next?
And then fluorine is in group 17, so it needs 7 valence electrons, and then times 4 because there's 4 atoms. So that simplifies to 28, and 28 plus 4 is 32.
Yep. 28 plus 4 is 32 valence electrons. So this is what we have. So step 1 is what do we have? If you had one word to explain step 1, it's the word have. Okay. Step 1, what do we got? Right? Awesome. You did that flawlessly. Good job. That person is sick today. They emailed me. Sia, do step 2 for me.
Okay, so there's 1 carbon atom, so that'd be 8.
That's how many it wants.
Yeah. And then there's 4, so you do 4 times 8.
And that gives me how many valence electrons does it want if it was a perfect world?
40.
Beautiful. You did that flawlessly. Look at you guys go. You were acting all scared and like you didn't know what you're doing. You guys are doing great. Jonavi, do step 3 for me.
Since it wants 40 valence electrons and there's only 32 available, then you subtract the 2 and get 8.
And what does that 8 represent?
How many they're sharing?
Shared. So if there was one word for step 1, it's have. One word for step 2, it's what do they want. The one word for step 3 is what do they share, right? So you're subtracting. All right. And then take me through this last step. You did that beautifully. Well, the last step here. Faisal, what do I do now? Step 4.
So since you have 8 valence electrons, they're in bonds, so you can have 4 bonds, I think.
Yep, is 4 bonds. So each electron goes into a pair of shared electrons because each bond is equal to 2. So we have 4 bonds available for this molecule. If we do 4 bonds and then satisfy everybody else with dots the way that we're supposed to, which is what this accounted for, then we should have the perfect molecule without having to guess. Beautiful. Awesome. Thank you so much. That was great. Next, Wajiha, what do I do now?
Do you draw it out?
Yep. So how do I start drawing? Which one's going to be in the center?
Is it carbon?
Yes, because carbon has the most sticky points, right? Carbon has 4 valence electrons. So if it was by itself, it would look like that. So it has 4 available to bond. And there's 4 things for bonding too. Also, we normally put the central atom first, right? So that's kind of 2 ways you can tell. Okay. So Darshan, to answer your question, Darshan has a great question. He said, for the division set, could you just use the subscript and say that there are 4 bonds because of 4 fluorines? No, because double bonds and triple bonds exist. So this example is pretty, but like in the next example we do, you're going to have some double bonds. You're going to see why you can't just look at the number of bonded things. But in these 2 cases, I started with the simpler ones first to get our head around it. And then we're going to do one more that's a little trickier. Does that make sense? So we're slowly building here in complexity. Okay. So that C is in the middle. Wajiha did that perfectly. Bob, what do I do now?
So you'll draw the fluorine surrounding it. Like if carbon was in the box, I have the fluorine surrounding it.
Yep. And then what do I do? Go ahead and give me the next one.
Draw the lines connecting carbon to the fluorine, which equate to like 2 dots.
Yep. So we had 4 bonds to use. We used them all. We are done with our bonds. What's the second to last step to this process, Madison?
You check like if. Oh, sorry. Could you repeat the question?
Yep. So we did the bonds. What do we have to put on now?
Oh, the electrons.
All right. So where do I put them?
You do 2 there. And then, 2 there. You just do like 3 pairs on each fluorine.
How did you know it was 3 pairs on each fluorine?
To make to make 8 valence electrons because the line is 2.
Yep. So this line already accounted for the first 2. We only need 6 more. Okay. And we put the dots along the outsides of the box, right? That imaginary box that's around each atom. Beautiful. All right. So I'm done, right? Yeah. Totally done. Super done. Eva, am I done?
No.
Why am I not done? I did so many things. This takes forever.
You need to count your electrons to make sure that you have the right amount.
Okay, so what number should I be looking for here?
32.
So I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Beautiful. We did it right. Good job, guys. Go team. All right. Yeah, no problem. I'll always explain. Oh, that makes me feel good. I don't get thank yous very often. That just made my heart smile. Okay. All right. Someone just thanked me for explaining things. So CO2, this is one of those ones that gets a little trickier. Okay. A little bit trickier, a little bit iffy. This is our last example. Okay. So I'm going to give you a minute or 2 to work through it. And you're going to see what I meant, Darshan. I want you to think about what I said. Okay. So you're going to see what I meant about not just dividing the number of atoms to find the bonds. Okay, you have about minute 30 left, according to the timer. All right, about 30 seconds left. All right, we're gonna start the wheel. We are almost done, so everyone's gonna get through the wheel. Kiera, start me off. What's step 1?
So you would have 1 carbon plus 1 or plus 2 oxygen.
Yeah.
And carbon has 4 valence electrons and oxygen has 6. So you would do 2 times 6.
Beautiful. So how many is that total?
And that equals 16.
Beautiful. Good job, Kiera. Woo! Step 1 done. Step 2. Celine, tell me what you got. Step 2.
So for the wanted, I got 24.
How did you
because
The carbon wants 8.
Okay. I think there's a little bit of lag, but you had the right number.
And then the oxygen wants 8 also, but it has the 2 atoms.
Yep. You're kind of coming
So
through
2
lagging.
times.
Did I write it right? You came through kind of spotted for me. I don't know if it was like that for anyone else, but I think I heard you. And yes, you were right. Each of them wanted 8, the carbon and the oxygen. We write it like this because we learned with hydrogen, some of them want 2 or other numbers. So we don't want to mess that up, right? All right. So next, good job, by the way. All right, Snehag, what do I do next?
So then you have to find the difference. So you do 24 minus 16, which is 8.
8 valence electrons. And what does that represent, that 8?
So those are the electrons that are shared. So you would divide that by 2 in the next step.
Okay, yeah. So the next step, you'd have 8 valence electrons, and then there's 2 valence electrons per bond. So that's 4 bonds in our molecule. Awesome. Beautiful. All right, Sangeet, what do I do now?
So because there's only 2 oxygen molecules, you're gonna have a double bond. And so you're gonna start drawing it with the C in the middle.
Yep, C is central. C is always central,
And
but
then
given the option, C is just kind of like that. Go ahead.
and then the 2 O's are going to be on the left and the right.
Yeah, it could be left, right,
And-
yeah, or it could be top, bottom, either one. All right, go ahead.
And because there's 4 bonds, you're going to have double bonds because there's only 2 molecules of O. And then the lone pairs are going to be on the oxygens.
Yes, so how many lone pairs do I do?
2 on the bottom and then 2 on the top, and then the same for the other molecule.
All right, so Maheen, check our work.
Well, you would count all the electrons to see if it's how many you need, and you would 15. So,
Yep. So we
isn't-
count 2, 4, 6, 8, 10, 12, 14, 16. That's what we had to work with. Ooh, hello. That's what we had to work with. So we are good to go, right? And what's the last thing that we check? Samir, what's the last thing we check? We checked the number of valence electrons. What else we gotta check?
I'm thinking the can I get a hint?
For individual atoms. The whole molecule has 16. That's great. How many did each atom want?
Oh yeah. So the oxygen wanted 4 and the carbon wanted no. Oxygen wanted 2 and the carbon wanted 4.
Yep, the carbon wanted 2, the oxygen wanted 2, the carbon wanted 4 because they wanted a total number of what?
24. Or well, 8. Oh well, yeah. Okay, so 8.
I see what you're doing. You were actually making it way harder than my question was, and you were thinking ahead, and I love that. So you're actually giving me the harder answers to the question I didn't ask, and I fully appreciate that. Like, that's amazing, right? So I was going for the simpler answer of each atom needs 8 electrons, and just to count around to make sure. But you were like going through whole molecule and making sure everything was transferred and everything else or whatever, or shared right, and that was beautiful. So thank you for that wonderfully beautiful wrong answer. All right, so we have 2, 4, 6, 8, 2, 4, 6, 8 for carbon, and 2, 4, 6, 8 for oxygen. All right, so now that we've learned the rules, Darshan, this is why we can't just look at the number of atoms and say that's the number of bonds, okay? So double and triple bonds exist, and double and triple bonds are actually shorter and stronger. It's like tighter wound rope, right? So the molecules are a little smaller and they're stronger and harder to pull apart, okay? So with all of this being done, hold on, let me check the chat, make sure that's not a question. When would we use a triple bond? There are molecules that like triple bonds. Okay, so for example, I know cyanide ion has one. But basically it's when we have to share. It's usually nitrogen. Nitrogen really like triple bonds, things like that. But let's take a look at this one. Let's do, let me get a blank sheet real quick. So before I do that one, does it matter where we put the lone pair electrons on the double or triple bonds? The lone pair electrons have to go on the atoms that aren't satisfied. And it didn't matter. I could have drawn them like on the top and the right, or the right and the bottom. I just draw them like that because my brain likes symmetry. I have a math brain, right? And then it's a double bond because we have to share 8 electrons for everybody to be satisfied. So if we didn't double up, there would be no way for us to share 8 electrons to be satisfied. We wouldn't be able to make up the difference between what we have as a group and what we want to do as a whole. Does that make sense? So those were the 3 questions I think were in there. Okay, so for a triple bonded example, does everyone have this? I can just erase what's on this slide and use this as like a template. So if I do C2H2, now this is an organic compound, I'm not going to make you do it. The 2 C's are central, the H's are on the outside. So if we do our process, right? So we have 2 times 4 plus 2 times 1. So that gives us 8 plus 2, that's 10 valence electrons to use. But if we had it, because this is 2 C's plus 2 H's, right? If we were to do our formula, 2 times the 4 valence electron, or sorry, 2 times the 8 that carbon wants, plus 2 times the 2 that hydrogen wants, because it's the 1s shell, means that in a perfect world, we would need 20 valence electrons, right? So we have 2 times 8 is 16, plus 2 times 2 is 4, so 16 plus 4 is 20. So that means that we're sharing 10 electrons because of the subtraction of the 20 minus the 10. And that means that we would have 5 bonds because it's 10 electrons divided by 2. So we have 10 bonds to use here, right? Hydrogen can only have how many? 1 bond. Can I put a double bond here ever? Let me ask last 2 people. So Ray, can I put a double bond between C and H?
No,
Why not?
because hydrogen only has 1.
Hydrogen only has 1s shell, which means it can only have 2 electrons total, right?
Yeah.
It can only have 2 electrons. So this bond is all of the electrons it can have. Same for this one. So if I need to put 5 bonds down, what has to happen between the carbon? That's when we see our triple bond.
Yeah, okay.
Yep. Does that make sense? So that used 10 electrons. We only had 10 electrons, right? 2, 4, 6, 8, 10. So this would be our whole molecule. So it's H, C, triple bond C, H. So it does occur. It just happens a lot more with organics and nitrogen. Okay. All right. The last thing we got to go through is the exceptions. So you had these in your notes. I just want to verbally talk about them. We just talked about hydrogen again. This is because it's in the 1s, right? So it only has 2 electron spaces. Ignore this, Somar. I was just trying to show you that each bond had double the amount of electrons. So when you're counting, you would count 12. When you're counting, you would count 10. But you guys seem to have that really great. So just ignore that part for now. Boron only likes to make 3 bonds when it's the central molecule. So when boron is in the center, it only likes 3 bonds. This is because it's so close to the 1s shell and it likes to lose and some other things that we would talk about if you were AP or IB. But I just want to make sure that I verbally tell you boron only likes 3 bonds as the central molecule. These are a couple facts you do have to memorize, okay? So I've explained before that the higher you go in science, the more exceptions you memorize, and that's really what you're studying, is why things don't follow the rules versus what the rules are. The basics are learning the rules, and then we learn everything that defies the rules. Straight anarchy up in chemistry, okay? So boron defies rules, it has 3 bonds. Phosphorus, if we do phosphorus, it has 5 valence electrons, right? So if you look at the position of phosphorus on the periodic table, and I know you don't have to explain this on your test, but I want to show you. Phosphorus is in that 3rd energy level, right? So this is the first line that has a D shell available. Even though it's down here, the 3rd energy level has the D subshell in it. It is available. It exists for the first time, okay? So this line is where that D shell exists for the first time in quantum number 3. Does that make sense to everybody? Remember dropping by 1 and going down, okay? So what phosphorus does is phosphorus is super electronegative, right? Just like fluorine and all of them. So it's like, hey, this D shell has all these empty rooms it's not using. I'm just gonna borrow one. So I'm gonna make 5 bonds, and I'm gonna have each electron alone instead of pairing up, because I have all these empty rooms in the hotel I'm not using, right? It's like if you had a birthday party and you had 6 people go to a hotel and 7 people showed up, but the room next to you was empty, they would just book you in the next room. It's the exact same thing. So they're just using the extra rooms that are empty in that D shell to expand their octet. And it will always be 5. Phosphorus likes 5 because it has 5 valence electrons, and that's a great way to remember. Sulfur likes 6. Why do you think sulfur likes 6? Kate, give me your best guess based on what I just said. Kate, are you here? You were the last person on the wheel. I'm so excited I get to go through the whole wheel. It's okay. Does anyone want to take a guess?
6.
Okay, make 6 bonds because why?
Because there's 6 valence electrons.
Yeah, because sulfur has 6, right? And normally we would never write it like this because it's violating the box rule, but where are they borrowing from? Who are they borrowing from? Where are they borrowing from? Which subshell? Anybody? Think about your periodic table. Which part do we skip a lot because it's weird? Yeah, the D block. Thank you, Eden. They're borrowing from 3D. This is the first time a D shell has existed. So it's borrowing, actually, this is borrowing 2 orbitals. And this one's borrowing 1 orbital from 3D. Okay. All right. Those are all the exceptions that you have to know. Basically, xenon will also bond sometimes, but I'm not going to have you worry about that. Are there any questions? I know that took a little longer because you guys asked some questions and we actually did an extra example. So that's great. Are there any questions for the whole group? Because if not, I'm going to let everyone go and then we can have individual one-off questions if you need them. Okay, guys, thank you so much for working hard and staying and going through all of this. I really hope it helped and that you really understand. Remember, your stuff isn't due until Friday because of my digital snafu. So if you just want to focus on benchmarks, that's cool. If you want to get it done early, also cool. Just do what you do. Okay. All right, guys, have a great day.
Thank you.
So is the only homework due the activities and the video on Friday?
Yeah, so on Friday we have the benchmark. So I adjusted the Canvas module so that everything is done. You shouldn't have videos to watch before your benchmark. I don't think. It's just videos to watch for Monday. I thought I fixed all the little errors when I was porting everything in, but I'll go look at Canvas again. But you have your benchmark next class, and all of the asynchronous from today isn't due until 11:59 on Friday because of my technology issues.
So we don't have a quick check due on Friday?
It will be. It's the QC 4.3 once it gets fixed. But it's Friday at midnight. Like, so you're not going to have another lesson between then and now. It's today's quick check, but it's broken. No problem.
Miss Longley,
Yes.
for the learning summary, does it have to be, do the sketch notes have to be hand drawn, or can they be done online and then shown.
I've had people use like art programs on their iPad and things. That's fine. If you want to create something, it's just something you physically create. I don't want you to like, I don't want you to create, like find things in Google and copy paste images. Like I actually want you to,
Right.
if that
Okay.
makes sense.
Yes, ma'am. Thank you.
All right. Any other questions?
Yeah.
What's that?
So for me, can you like just, I mean, it's just, can you go over the, like what the the exclusions mean again? Like you said stuff about D block and I just got completely lost.
Yeah, so let me go to P table. Let me actually pull that up. Okay, so this is the 3D section, correct?
Yep.
It's in the fourth and we subtracted by 1. So all that's meaning is that the third energy level has S, it has P, and it has D, right? But phosphorus and sulfur are the first elements that are non-metals that are in the third energy level. So these still exist, they're just empty. It's like a hotel. So the orbitals are there. Those 3D orbitals, all of those spaces for those 10 electrons exist. There's just no electrons in them. Okay. So what phosphorus does is says, yes, I only have 4 sides available to bond, but I'm going to borrow one from the 3D since they're not using them anyway. So it lets every single individual valence electron of its 5 pair with someone else. So phosphorus actually ends up with 10 electrons around its central molecule instead of 8, because it's borrowing spaces from this line, which 2D did not have access to. I know that's actually an AP concept. You don't have to know why, you just have to know it is. So if you know that phosphorus is 5 and sulfur is 6, that's as much as you have to know for pre-AP.
Okay.
Yeah, the why is an AP concept, but I like telling it to you anyway, just to be sure, you know, like, so people who want to know can know.
Yeah. So by 5, do you mean like 5 bonds?
Yep.
Right?
Phosphorus likes 5 bonds when it's in the center because it has 5 valence and every valence electron finds a buddy. Sulfur likes 6 bonds.
Okay.
Yep.
I'm kind of struggling with this, but I think
You are not
I'll figure it
alone.
out, or-
I had to review this with my HL babies for IB as well. Like it's one thing that like, even when you get it that day, like you come back to it and be like, this is really a lot. That's why I gave you guys really clear steps. Cause normally to say, hey, count the number of valence electrons and use them all until they have 8. And it's like, well, then you're just kind of like guessing and like, so I wanted to make sure you had a concrete process to follow.
Yeah.
Yeah.
Okay.
It's gonna take practice. This is one of those things that it's like literally just straight practice. It's gonna take time.
Yeah.
Mhm.
Well, thank you.
No problem. Have a good day.
You too. Bye.
Bye.